In this video, we're going to be looking at segment links. In particular, we're going to be looking at pairs of segments that could either be chords, secants, or tangents, and how they interact with each other when they're placed around or inside of a circle. In the video, we're going to be looking at three different situations. The first is going to be called segments of a chord theorem. When two chords intersect in a circle, each chord is divided into two segments called segments of a chord. Let's go ahead and take a look at that picture. All right, so I'm going to go ahead and start off with a center for a circle. All right, I got a picture of a circle here. And according to the prompt, I'm going to need two chords that intersect inside of the circle. Okay, let's go ahead and let that be one chord, and I'm going to go ahead and choose a second color for the other one. I think that might show up a little bit better here. Okay, let's go ahead and name some points here. Let's call that A and B. Let's go ahead and call that C and D. And the point in the middle, let's go ahead and call that just point P, just some point where they're meeting up there. All three of the theorems that we're going to look at in this video can be proven using similar triangles. One of them is a little bit easier to prove than the others, which is going to be the one that we're looking at first. However, for the purpose of the video, I'm only going to be providing the actual theorems for you, not the proofs. Okay, so for the first one here, when we've got two chords intersecting with each other, they divide each other into what we call segments of the chord. So you have a segment here, AP, you have a segment here, PB, you've got CP and PD. The theorem that we're going to get out of this is that the product of the segments of the chord taken from the same segment will be equivalent to the product of the segments of the chord taken from the other chord. All that might sound a little bit crazy, but here's what it says. If you take the length of AP and you multiply it by the other part of that chord, which is BP, it will be equivalent to CP multiplied by DP. Okay, and again, that can be proven using similar triangles. The proof generally looks like this. If you were to connect AD together and connect CB together, you can prove that those would be similar triangles. Then based on proportionality, you could take these segments, set up a proportion, and with cross products, you get this. All right, for example one, let's go ahead and apply the segments of a chord theorem. What we have are two chords intersecting at point N, each of which is broken into what we call segments of a chord. You've got KN and you've got NJ, where KJ is broken apart. You've also got MN and NL, where ML is broken apart. So if you take the product of X and X plus 4, that will be equivalent to the product of X plus 2, X plus 2, and X plus 1. Then with a little bit of algebra, we can figure out what X is, and after that, we can figure out what ML and JK equal. Okay, with a little bit of distribution here, we get X squared plus 4X. Over here, with double distribution, you get X times X, which is X squared, X times 1, which is X, 2 times X, which is 2X, 2 times 1, which is 2. Okay, now we can do a little bit of grouping, and we can also do a bit of canceling here. Both sides of the equation do have an X squared, which we can cancel out. You can just basically subtract the X squared from both sides. We then have 4X is equal to, that can group together as 3X, so you get 3X plus 2. Go ahead and subtract the 3X, X is equal to 2. Okay, not the answer to the overall question, but is going to be necessary to figure out what ML and JK are. Okay, so ML is going to be equal to X plus 2 plus X plus 1. And of course, if X is 2, that makes this 4, that makes that 3, which is going to give you 7. JK is going to be 2 plus 2 plus 4, that's a 6, which is going to give you 8. Our second theorem is going to be the segments of secant's theorem. For this, what we're going to have are two secant segments that meet on the outside of a circle. A secant segment is a segment with one endpoint on the circle and the other outside. Okay, what we're going to be looking at is two secant segments that meet on the outside using that outside point. The circle itself will divide the secant segment into two parts. One part will be a chord, and then the other part is called an external segment. Okay, here's what this looks like. We'll go ahead and start with the center, just so that we have one. Here's a circle. A secant segment could look like this. Okay, it has an endpoint on the circle. Let's go ahead and call that A. It has a point on the outside, an endpoint on the outside here. We'll go ahead and call that P. The part that we have from A to here, let's go ahead and call that B. That would be a chord, and then this would be the external segment. What we're going to go ahead and do is add in a second secant segment that meets up at point P. Okay, so it can be located wherever you want, as long as it has an endpoint here. Let's go ahead and just connect in that spot. We'll call that point C, call that point D. The theorem here is going to be a little bit different than the last one, but also a little bit similar. It is going to involve two products being set equal to each other. But the products are not going to be the broken up parts that we have from our secant segment. Instead, what it is going to be is the entire length, AP, multiplied by the outside portion, by the external segment. Okay, and that's going to be equal to the entire length here, CP, and the outside part, DP. Okay, so be very careful here. It's not the individual parts are being multiplied. It is the whole length multiplied by the outside length. Again, this could also be proven using similar triangles, but for the purpose of the video, I'm just going to be providing the actual theorems. For example 2, we're asked to find the value of x. We do have two secant segments that are here. Using our theorem, what we can do is set up an equation and solve for x. From the top secant segment, what we're going to do is take the total length here, which is 16, multiply that by the outside length, which is 6. Okay, so again, it's not going to be 10 times 6. It's going to be 16 times 6. That would be equal to the entire length here, which we have to describe as x plus 8, multiplied by the outside length, which is 8. 16 times 6, you can simplify that at 96. You could distribute the 8 in if you want. However, because 8 is just a factor on that side, if you want to, you could actually just divide it into the 96. Okay, so I'll just leave that as it is for a moment. Divide out the 8 here, which is going to give you 12, and 12 is equal to x plus 8. Okay, and that could be a little bit faster than distributing, subtracting, and then dividing. From here, we can figure out by subtracting 8 that x is going to be equal to 4. For our third theorem, we're going to look at a combination of using a secant segment and a tangent segment. Okay, let's go ahead and start with a picture of a circle. All right, as shown before, a secant segment is just a secant that has endpoints with one on the edge of the circle, the other outside. In which case I'll label the same as I did before, A, B, and P. What we're going to add in here is a tangent segment that meets up at point P. Okay, so measuring off to this side, you could actually do it over here as well, but it would be a really tight picture, so I'm going to use this side. All right, so from P to the point of tangency, that'll be the endpoint. Right there, we'll call that C. All right, so a difference that we do have here is that this doesn't actually have two parts to it. It really doesn't. It doesn't have two parts. All right, the secant segment does have two parts, and if you relate that one to the last theorem, what we would start with would be the whole length multiplied by the outside part, and you're going to keep that. Okay, AP is going to get multiplied by BP. It's going to be the whole length multiplied by the outside length. Of course, your tangent segment doesn't have two parts to it, but it does have a whole part and it also does have an outside part. It just happens that the whole part, CP, is the outside part, so this will be CP squared. For example 3, we're asked again to solve for x. We do have a secant segment and we have a tangent segment. The secant segment, we're going to take the total length, which will be 12 plus x, except I'm going to write that as x plus 12, just because we're used to seeing it that way. We're going to take that total length and multiply it by the outside length, which is x. That I'm going to go ahead and put in the front because we're going to use a little bit of distribution. That would also look a little bit better in that spot. That would be equal to the tangent segment squared. X plus 4, you could raise it to the second power. For the sake of demonstration here, what I'm going to do is just go ahead and expand that out so you can see it written twice. Okay, now with distribution, we can distribute the x in here, which gives you x squared plus 12x. Here, with double distribution, you get x and x. You get x times 4. You get 4 times x. You also get 4 times 4. Okay, and like in example 1, the x squareds are going to cancel. You can take those out. You can also group these together. So you get 12x is equal to 8x plus 16. Subtract the 8x. 4x is equal to 16. And by division, x is equal to 4.
Wait, there was.